Hello everyone, my name is Chunlin Tian, a PhD student from University of Macau. It's a very honor to present our work named Kahou. That's a software-hardware co-design solution to address the challenge of running LLMs and the resource-constrained edge devices. This is outline of today's presentation. Let's begin with the background and motivation. The first question is why deploy LLM on device? The motivation is to process the data closer to where it generated. By running the model on the end-user devices like the phone, PC, and IoT devices, we gain real-time response and protect the privacy. Unlike the cloud learning that we should send the sensitive data to the cloud so that the LLM on device is the next layer of AI, which not only enhances the privacy but also improves the latency. This is important for real-time decision-making. Moreover, reduce the dependence of the network and can lead to more cost-efficient AI devices. However, directly deploy LLMs on the edge devices is not straightforward. There are several challenges of the edge workload. Here we list the three main challenges. First is the high memory footprint. For example, we deploy the billion parameters model into the resource-constrained edge devices is running to the out-of-memory errors. Secondly, there is a high computing bound. For example, we process a request with 11 tokens across the Llama model. Requests the flops almost 300 times than the traditional VGG-90 model to process a single image. And last, a difference from the cloud server. For the edge devices, energy is very sensitive, and the application supported by the large AI models expand the energy cost. For example, Google search with the AI model will reduce almost 30 times energy cost than the standard Google search. So energy is a very important question for the edge devices. So what should we do to address the above challenges to efficiently deploy LLMs at the edge? To explore the opportunities, we have done following experiments. First, we decouple the LLM's transform layers and analyze the layer 1 sensitive one by one. From those figures, we compare the layer impact from the generative ability, energy, and latency. And we can see that some layers have more important to the performance or the compute. Therefore, the first opportunity is that the layers with the same architecture have heterogeneous impact. Secondly, unlike the traditional DL models with the fixed input and output format, for the real-time LLM request has the dynamic params and output lengths. This from the figure A is displayed a real application trends to analyze the distribution. And moreover, this dynamic variance will lead to the dynamic memory and latency and the inference energy that distribution. So that the second opportunity is the dynamic I/O with the max text request and need the precise inference service. Apart from the model level and the text level heterogeneous, the third is about the platform. For different applications, may have different LS requirements. And for the different hardware devices, here we use the Nano and the NX. Have various impacts. Even with the same task and the same hardware platform, the can running foreground application. Here we use a web search application. Also may lead to the runtime variance. So that's the third opportunity is the hardware type, runtime variance, and LM application SLC may impact the end user QoE. And here we try to adjust the process frequency to explore the impacts on the inference latency, end-to-end latency, and the per token latency, and the energy cost. So that's the frequency proposed opportunity to optimize this inference from a system level. Based on the opportunities, next we will walk through the design of the clone. The architecture of clone, which can be divided into two stages. First is the offline device-specific tiering, that we tire the warning LLMs into a deployable LLMs, then porting it to the edge devices. For the second stage is the online latency aware inference, that's based on the end user makes task request. The edge devices dynamic adjust the adapter and frequency to meet the user's requirement and keep the model performance. Then we detail the design of each component. First, for the offline pruning. Unlike the traditional pruning method that all often assume the same importance across layers and only focus on the performance improvement, Clone use a metric that combines the energy cost and ensure that the model fits the real-time construct of the edge platform and keep the generative abilities. So that Clone first gathers the data pairs, link the layer-wise pruning or the structure pruning to performance the score based on the objective, so that we can factor a series of the ratio score pairs. Then based on this those pair data, we use a encoder, evaluator, decoder architecture to embed the pairs into a space enable smooth exploration beyond the discrete heuristic method. And then we use a gradient assist process to identify the best pruning configure embeddings in this space. Then we use the decoder to generate the follow layer-wise pruning ratios when being searched. Based on this pruning ratio, we conduct the structural pruning tailored to the construct devices to meet the memory budget. After porting the pruning model at the edge, we then discuss the online stage. For the real-time inference, the end user requests often with the max tasks, so that we develop a event router that we regard each downstream task as an expert and fine-tune it with the low-rank adaptation, that's LoRa. Based on the random input, Clone use this event router to rebuild an optimal adapter to improve the performance. Meanwhile, for the real-time system, the controlling applications may also lead to the runtime variance, so that we need a token level learning-based DVFS use the reference learning. For the DVFS controller, unlike the traditional method that regards the all model as a black box, a clone adjusts this FV at each token level and use the per token latency, that's the TPOT construct, to guide this all process. To effectively translating the soft optimization into the real-world performance improvements, a clone introduced a scalable hardware accelerator, including a LoRa processing unit, LPU, for the dynamic adapter head swapping enable adaptive model optimization, and a spatial function unit that's including the device controller, so that to performance fine-grained the device adjustments at the decoding token level. And this figure shows the physical layout of the spatial accelerator. And the right figure shows the test time that the connection of the AI chips and the JSON processors. Next, we examine the evaluation results on the multiple edge devices and the benchmarks. Here is the detail of the infrastructure, including edge devices and various base model and representative benchmarks. First, we compare the text generation abilities across several models and different model customization technique. From this result, we can see that Clone preserves the most generation ability. This is due to first, we use generation ability as a pruning metric to get the pruning ratio selection. Secondly, we use the gradient-based optimization to identify the optimal pruning configuration. Beyond the generation, we next evaluate Clone for the real-time text-solving benchmarks and BBH and MU and the common sense tasks. We can see that Clone always significantly outperforms the other baselines across all the baselines. This is due to that it uses the text-aware tuning for the specific device, and secondly, it developed a request-wise MOE router, so that it can rebuild the optimal adapter for the max take request. To explore the robustness and the scalability of Clone, we evaluate different type of model and different model size. We can see that Clone consistent outperformance the baselines. So that Clone is not just limited to specific LLMs, not a one-shot software ask. We also evaluate the system efficiency of Clone. From this table, we can see Clone outperforms the baselines by speed up the inference process and saving the energy cost. The reason is that first, a clone don't consider the latency and energy as the metric to get the offline pruning process. Thirdly, for the online inference, a clone decouples the profile and decoding stage and apply a learning-based DBFS to improve the system efficiency. Thirdly, that the spatial accelerator can boost the efficiency by exploring the hardware improvement states. Here we also design evaluation study to discuss each component of clone, and more detailed results can be found in our paper if you are interested. Finally, let's summarize the key contribution and funding of clone. Firstly, clone proposes a source hardware core design for the efficiency LLM inference at the edge. Thirdly, clone uses the offline-online optimization to adapt the static and dynamic inference, supported by a specialized accelerator. Lastly, this work was evaluated through a representative benchmarks and across various base models. Okay, thank you everyone. If you have any question, please send an email to me. Thank you.